Hey everybody, thanks for joining today. I'm gonna wrap up the talk that I started last week about cellular architecture. I'll try to do a quick synopsis of the things that I covered last week so that this talk will be able to stand on its own. But if you're interested in um, diving into more details on some of the parts that I'll gloss over quickly in this talk, you can check out the recording of the previous one where we dive deeper on the original subjects. So, um, before I get started talking about cellular architecture, I'm going to do a quick little tangent here to talk about automation. So, I wanted to highlight some interesting moments in the history of automation. In 1436, the invention of the printing press allowed us to communicate at a scale that we had previously been completely unable to do. So that was a huge event. A little bit lesser known one in 1475, the invention of the cookie cutter. So we didn't have to carve out each gingerbread man painstakingly one at a time. In 1901, another well-known one, which is the assembly line. This is often associated with Ford Motor Company and the ability to mass produce like automobiles at a scale that we had never been able to do before. And then last but not least, in 2019, a path to escape YAML for infrastructure as code. This is obviously a little bit of a tongue-in-cheek joke here, and you may be wondering, I thought this was going to be a talk about cellular architecture. Why is this guy going on about automation? Well, I kind of covered this a little bit in part one, but we're going to get a lot deeper into it today. I believe that in order to have a maintainable solution for managing cellular architecture for your application, automation plays a really key role. It's really crucial to be able to figure out how to automate a lot of the repetitive tasks in order to make sure that you can manage all of the cells that you create without consuming too much engineering time. So I'm going to be kind of tying these two concepts together quite a bit in the talk today. So as I mentioned last time, my most recent jobs were at Puppet, where I kind of learned all my introduction to infrastructure as code and a lot of the principles of DevOps that have helped me form the rest of the foundation for my career. Then I worked at AWS for about 5 years and worked on a video streaming service where we were one of the first services inside of AWS to use cellular architecture from day one, based on the lessons that we learned from the bigger, more established AWS services. And now I'm a software engineer at Momento, where we have serverless products like caching and PubSub. And I was involved in the engineering team that built out the original cellular architecture for Momento as well. So that's my background. I covered this a little bit last time as well, like what is cellular architecture and why you should use it. If you're interested in more of a recap of that, you can check out my previous talk or this great talk from Peter Vachel from AWS, where he talks about minimizing the blast radius of failures for your distributed system. And the key concepts that he talks about are, as everyone who's used AWS for any period of time knows, there's the regions and availability zones that they give you as building blocks that you can use to design your architecture in a way where a failure at any one of those two levels isn't necessarily going to mean your service is entirely unavailable. And then he talks about cells, which is what we're talking about in this talk. A cell, for the purposes of this talk, is just an isolated deployment of your application that can serve requests independently from other cells of your application, so that if you have what Peter calls a black swan event or a poison pill event, and you get an unexpected type of request into your system that causes a bug or overloads some part of your infrastructure, it may cause an outage in that cell, but that will only impact the customers that you have in that cell, and the other cells that you've created will be unaffected. So it's a mechanism for deciding how to deploy your application in a way that will minimize the amount of impact that any given customer has when some type of outage occurs. And so this is the list of goals that I wanted to talk through about how to create and maintain a cellular architecture for your application. We have to figure out how to solve the isolation problem to keep our cells separated from one another. We have to figure out how to create new cells, how to monitor all of our cells, their health and utilization across the whole scope of our cells, rather than having to check on each one individually. And then, and we talked about all three of those in my previous talk. So I won't go into those quite as much today. Today we'll be focusing on these last two deployments. How do we manage deployments to all of these different cells and permissions? Who can access the cell and what does the cell have access to? So before we get into how to solve those particular problems, we want to talk about standardization a bit. And this is kind of the main way where we're going to tie back the two ideas of cellular architecture and automation together. In order to automate things about the life cycle of your application in these cells that you create, you have to find some places where you can standardize certain parts of your app so that you can write generic infrastructure code that can interact on all the different components of your service and manage the life cycles of them in a consistent and standardized way. And so we talked about a few of these last week that I'm just going to gloss over really quickly. We talked about standardizing build targets. So if you have multiple microservices that make up your application, it's really powerful to come up with some standard way to define the build targets for their different life cycles. And at Momento, we do that using make files, so we can have a consistent set of make targets that can be reused across all of the different types of microservices. Another thing that we talked about is a cell registry. So I described how we model the data about all the cells that we create, and we keep this data in a centralized place where we can access it from any of our infrastructure code, so that our infrastructure code always can find whatever data that it needs about a given cell in order to manage it. And this was a slide showing an example of an instance of that data for a given cell in our cell registry. We talked about creating a cell bootstrap script where your application is made up of many components that are probably defined as their own unique Git repos or packages within a Git repo, and how you can write this generic logic. Once you've done some standardization, you can write some generic logic that can grab information about a cell from your cell registry and then iterate over all of the different components of your application, all of the Git repos for the components of your application, and run one of your standardized make targets against them. And that gives you this really nice generic way to manage the lifecycle of all of your components, even if they are built very differently from one another. So we talked about all of that stuff last week. This week, I want to talk about some standardization that is useful for handling deployments. So deploying the various components of your application into a cell is really one of the most challenging problems to solve when you're trying to come up with a generalized cellular architecture. So we're going to talk about how we can standardize that a little bit. But I want to call out before we get into it that when I'm using the word standardization here, I do not mean homogenization. And so the distinction I'm trying to make there is that if your application is made up of a whole bunch of different microservices or several different microservices, there is no requirement that all of your microservices have to be built using the same exact tech stack. And in fact, it's pretty unlikely that that will be the case. Over time, you will find different technologies work better for different types of microservices, and you want to be able to use the right technology for the right purpose. And so it's totally fine to use different tech stacks for your different microservices. Here we have a few different examples of flavors that we might be using. One is some serverless resources, an API gateway, Lambda, step functions, DynamoDB, that could all be deployed using a CloudFormation stack. Another example is a Kubernetes application where you have a load balancer, some application containers, some database containers, and the deployment of those gets managed by Kubernetes. Then I have a few more CloudFormation examples here. So the key is to figure out some things that these have in common and ways that we can standardize the different aspects of the life cycle of deploying all these different types of applications. So when we want to do a deployment of any one of these kinds of components, there's going to be a life cycle that looks something like this. So you're going to have a commit where you've made changes to the code for that component of your application. Then you're going to have a build phase where you're executing your build tools, producing whatever the final artifact is, making sure everything builds successfully. And you're going to have a release phase. And that release phase is where you publish the artifact from your build to a place where it can be used in the deployment of your to your cells. So that might be like a Docker image that's getting published to Docker Hub or to Amazon ECR, or it might be like a jar file that you're publishing to like a Maven repository. It depends on the type of application that you're building or the type of the component that you're building. And once you've completed that release phase and the artifact is available, then you start the process of deploying it to your individual cells. So you deploy it to one cell, then you deploy it to the next cell, etc. In actuality, since one of the reasons that we want to use cellular architecture is to minimize the blast radius of problems that might occur, it's important to also have the observation that deployments are one of the main times that you're likely to encounter some kind of problem or some kind of outage that contributes to the blast radius of an outage that impacts your customers. So it's important to be really careful about what's happening during your deployments. So we'll actually want to add a few more steps to our standard lifecycle here. We really want our first deployment to go to some kind of staging cell that isn't impacting customers. So if something goes wrong there, we haven't caused any issue to customers yet. Then we want to add another phase here that we call a bake. The bake phase is some period of time that we're just going to sit and not do any further deployments. And we're going to monitor our metrics and our alarms and make sure that the health of that staging cell looks good. And after some period of time, when we're confident that the change is okay, then we'll go ahead and move on to the deployment to the first production cell. And then we'll kind of repeat that pattern. We'll do another bake there to make sure that that looks okay. And then we'll continue deploying to the other cells. And if something goes wrong during that bake period, we can just abort the whole deployment. And that gives our engineers and our operators the ability to go figure out what went wrong and fix it without allowing it to impact more customers. So if we take this kind of standardized life cycle for deployment that we've defined here, and we go back and we try to figure out what tools and technologies we can use to achieve it for a given tech stack that we might be using for our components, we can come up with a general set of tools to use for different flavors of microservices or different tech stacks that we're trying to deploy that still all adhere to this basic model. So in this slide, I'm showing a tech stack that we might choose to use for a CloudFormation-based deployment. So for that commit phase, we can use AWS code pipeline to kick off all the machinery that happens when the commit is made. Then we can use AWS code builds for the build phase. This just gives us an environment to actually execute the build and produce the artifact. And then that release phase, for this particular example microservice, I'm going to assume that the release artifact is a Docker image. So we're publishing it to this Elastic Container Registry. And then the deployment we'll do using AWS CloudFormation. So we'll make a call to AWS CloudFormation to start deploying this change to our staging cell. And then AWS Step Functions is a really great tool that we can use for this bake phase. We can define like a Lambda that checks the health of all of our metrics and alarms. And then if they look okay, then it maybe sleeps for 5 minutes before it checks them again. And it just kind of loops like that until we've waited for long enough to have confidence that the deployment went okay. And then at that point, the step function can exit and move us on to the deployment to the next cell. And then we just repeat that process with CloudFormation and step functions. So these are technologies that we happen to have chosen for this type of deployment at Momento. But you can imagine swapping in your own different choices for any individual parts of these technologies. For example, this was a CloudFormation stack. If we had a Kubernetes application that we wanted to deploy, we might choose slightly different tools. So here we could still use code pipeline, code build, and the Elastic Container Registry for those first three phases. But then when we get to the deployment phase, rather than calling CloudFormation, we might have an AWS Lambda that's making a call to the Kubernetes API to actually manage the rollout of that new Docker image. And then we can use the same step functions logic for the bake and wait and make sure that our metrics and alarms look okay. And then we move on to using the same Kubernetes API calls via Lambda to deploy to the rest of the production cells. So this is a general idea. And the key here is having a consistent set of these life cycle stages and being able to define them as reusable mix and match components, where for any given tech stack, for a Kubernetes tech stack or a CloudFormation tech stack or whatever, we have like a version of each of these life cycle phases that we can just drop in, and then it'll basically produce the same deployment template, but supporting different technologies. And that's how we can mix and match different tech stacks in our deployments. Okay, so this is the same slide I showed earlier where I'm talking about the 5. Now that we've talked about how we might want to standardize some things a bit, I can get into the solutions to these goals that we're trying to achieve for managing our cellular architecture. And as I mentioned before, I talked about these first 3 last week, so I'm not going to spend a lot of time on them. We're going to spend these were the solutions that we talked about for those 3. And if you're interested in more detail, you can check out my talk from last week. For isolation, we just created a separate AWS account for each cell. And then we had to figure out how to route traffic to that cell using either cellular DNS endpoints or a routing layer. For new cells, we just have these standardized makefile build targets in the cell bootstrap script. For monitoring, we talked about really all you need to do is make sure that you have a dimension on all of your metrics that captures your cell name so that you can differentiate between metrics from one cell and another. So that's what we talked about last time. This time we're going to focus in on these last 2 goals down here, which are deployments and managing permissions. So deployments, and this is why I was making the joke about automation and infrastructure as code at the beginning. I feel like the leap forward that the industry has made in the technologies that are available to manage your infrastructure as code in the last 5 years have been huge leaps forward, and they really make a lot of these generalized infrastructure problems much easier to solve than what we've ever been able to do before. So the key breakthrough that I've seen in the industry in the last 5 years on this is the ability to define infrastructure using real programming languages. Prior to this, all of the infrastructure as code solutions used either some configuration format like JSON or YAML, or some bespoke like declarative configuration language like HashiCorp's configuration language to define the infrastructure. And you could go a really long way with this, but you always were sort of lacking these core capabilities that you have become accustomed to having in your toolkit as a developer. When you're writing your application code using a real programming language, there's all these build tools and artifact systems for managing dependencies that you have available to you that just weren't there for infrastructure as code. But in 2019, AWS released the first version of the Cloud Development Kit, which is referred to as CDK. And this was the first time that you could manage basically CloudFormation applications by writing just regular code in whatever your favorite programming language was. In 2020, AWS released another variant of this called CDKs, which basically does the exact same thing, but for Kubernetes environments. And so now you could use code in your favorite programming language to manage your Kubernetes infrastructure rather than YAML. In 2021, AWS did one of the things that I consider to be like one of their biggest and most influential contributions to the open source community in a really long time. And they pulled out this common library called constructs that was the foundation of both of the previous 2 bullets. And it provides this foundation for defining these resource graphs of your infrastructure. but without it being tied to a specific deployment technology like Kubernetes or CloudFormation. And so shortly after that, HashiCorp released CDKTF, which is built on that same constructs library that AWS open sourced, but it allows you to manage your Terraform infrastructure using your favorite programming language. So all of these things happened in the last 5 years, and now we have all these different ways to manage our infrastructure as code that just didn't exist before. This is an example of the difference between the two. So on the left, you can see before we had CDK available to us, this is the definition of a policy for an S3 bucket, like the permissions for an S3 bucket. On the left-hand side is the old like JSON representation of this that is the normal input to CloudFormation. And I cut about 200 lines of code out of this so that it would fit on the slide. But it's this really tedious, really hard to manage blob of JSON or YAML. And now that CDK is out here available, we can actually achieve the same thing in only 3 lines of code as what I showed on the right here. It's just so much simpler, so much cleaner. And really the key thing that I wanted to call out here is I can define this variable called org principles, and I can populate that any way that I want to using, this is TypeScript code. So I can populate that variable any way that I want to using normal TypeScript code. Then I can just loop over all of those principles in my organization and call grant read to give them this bucket permission. So it's so much more flexible and powerful and less mistake prone than the options that we had before. There were a lot of options available where people tried to provide like templating solutions for the YAML or the JSON, but they were still, it always still felt like you had one hand tied behind your back compared to being able to use the first class tooling of whatever your programming language is. This is another example of the power of this. On the left-hand side, you can see part of a class that we've defined in our TypeScript code. This class is an instance of this AWS construct, which is basically just like a collection of resources that we can reuse. And if I had all the code here, you would see that it basically goes through and creates like a security group and then some ingress rules, and eventually it would create some EC2 instances, and etc. But I can bundle this all up into one class, and then I can just publish it as a library to wherever I normally publish my TypeScript libraries. In our case, we publish all our TypeScript libraries to AWS Code Artifact, but you could publish them to npm.js or Artifactory or whatever. And then once it's in there, you can consume that library as a dependency, just like you would with any other TypeScript code that you've written for your applications. So I can declare a dependency on this, and then in my infrastructure, anywhere else I want to in my infrastructure code, I can just say new hotel gateway and create an instance of this class, and it'll create all of those resources for me. So it's just this packaging mechanism that fits right into my normal TypeScript ecosystem that is so much more natural and powerful than the options that we had when we were just managing YAML and JSON. So, so those are some of the key advancements that I think what I've been calling IAC++, because I'm a dork. The infrastructure as the new flavors of infrastructure as code. That's some of the advancements that we have available to us now. And so now we can take those and look at how that allows us to solve this generalized deployment problem that I have been alluding to earlier in the talk. So this is a little snippet of example code that creates a pipeline, a code pipeline using CDK. This is an AWS code pipeline. And you can see here that I'm just calling this last line of code. I say stages.for each, and then for each, this is an array of stages that I've created somewhere else in my TypeScript code. And then I can just say pipeline.add stage, and each one of those stages will produce one of the boxes in this diagram here. So the interesting part of this is now all the options that I have available to me for how I build up this stages array so that I can create this code pipeline. So the way that we do it at Momento is we basically just this very similar to how we defined a model, a very simple like set of interfaces in our TypeScript code that we can use to model our cell metadata. We also created a simple little model that models the stages that we want to use in one of these pipelines. And so here you can see a function that returns the stages for our main microservice, which is called our cache service. And the interesting parts of it are there's an array called releases that just has a list of like the actions that I want to take during this release phase in the code pipeline. And in this particular one, all I'm doing is one Docker deploy. So I basically defined this way to say, okay, for this microservice, when I get to the release stage, all I want to do is this one Docker deploy. Here's the Docker file, here's the Docker image name. And that's all I really have to provide to differentiate this microservice from what we might do in the release phase for another microservice. And then here in this stacks array, we manage what we're going to do during this deployment phase, this deploy for each of the cells that we need to deploy to. And so here at Momento, we actually deploy our service to both AWS and GCP. So what I've got here is one AWS CloudFormation stack and a little bit of metadata that our pipeline needs in order to know how to deploy that CloudFormation stack. And then I've got a second stack down here that's for GCP, which actually ends up using Terraform, CDK Terraform to do that deployment rather than CloudFormation. So we just got this model here that tells the differences between the different stages. What is unique for this one service about these lifecycle stages? And that's all that I have to define about it. So then we have this thing that we call the pipeline of pipelines. And what that does is it basically just loops over all the different microservices that we define. And for each one of them, it builds out this pipeline using the different metadata that we saw in the last slide. And so at the end of that, I end up with one pipeline for each one of my microservices. And also, if I have any core infrastructure that has shared resources like VPCs or shared database resources, we'll end up with the pipeline for that as well. Now, each one of these pipelines may differ slightly from one another based on whether it's a CDK deploy or a Kubernetes deploy, et cetera. But almost all of the infrastructure code that I use to create these pipelines can be shared across all of the microservices so that there's very little work to do to add a new one and handle and make sure that the deployment strategy is consistent across all of them. So the pipeline of pipelines, it gives us one repo that contains all of our pipeline infrastructure, which is really valuable because if you need to add a new service and you need to manage the deployment for it, there's always one spot that you know to go to. And it also means that anybody who's really interested in keeping track of what's going on with your deployments can just watch that one spot to see when somebody makes an interesting change that's going to affect your deployments. This also allows us to reuse, as I mentioned, reuse these little building block deployment steps across all these projects. And then an interesting trait is it gives us a single source of truth for the deployment order. So as I've been showing in these slides, we tend to have these pipelines set up where it's going to do like a deploy to a staging cell first, and then to our first production cell, and then to our second production cell. It's really valuable to have that order be consistent across all of the different components that you're going to deploy so that they all have that same list of cells that they're going to deploy to in the consistent order. And so we actually have one little spot in our pipelines code that defines all of that. We have a list of cell waves, and the first wave we do our deploy to our two alpha cells, our AWS alpha cell and our GCP alpha cell. Then we have a next wave that deploys to our first production cell. For this one, we pick a cell that has pretty low traffic, maybe not a lot of customers in there, so that if something does go wrong that somehow got past our alpha cells, then the blast radius is limited. It's not affecting our biggest and most important customers. And then the next wave, we add a few more production cells that maybe are still low traffic, and then we start deploying to the big important cells. So by that time, we've got quite a bit of confidence that the change that's rolling out is going to be pretty safe to deploy. So having this one spot where we define all that is really powerful because when we add a new microservice or a new cell, we know that all the pipelines will be rebuilt to have the same consistent order. Okay, so how do we solve the deployment problem? It's a combination of a lot of things, and there's a little bit of complexity to it, but we have an account registry that keeps track of all of our cells. We use CDK to define some generic building blocks for pipelines, and then we can loop over all the microservices and loop over all the cells to define these consistent pipelines that have a standardized deployment pattern for each component that we're deploying. Okay, so now we're going to move on to permissions. Permissions, when we're talking about permissions in the context of cellular architecture, there's kind of two things. There's who has access to do things inside of a given cell that we've created, and what resources can that cell reach out to. So it's inbound permissions and outbound permissions. And as far as the inbound permissions go, the main things that we need to be able to support are allowing our developers to have access to the cells in order to do operational tasks. So like when someone's on call, if they need to dig into some logs in one of the cells, we need to have a story for how they get access to that. And the way that we do that, I mentioned some of this in my previous talk when we were talking about isolation and how we use an individual AWS account for each one of our cells. We also have an individual AWS account for each of our developers. And that allows us to give each developer a set of permissions to all of the different cells. And we can kind of use their account ID as their identity. So we can do all of this through AWS's SSO service, which is, I think, now been renamed to IAM Identity Center, but I can't ever remember to say that. So I still always call it SSO. But it gives you this splash page where you can authenticate using even like your Google identity. And then once you're logged in, it knows all of the different accounts that you have access to. And for each account, you may have a few different roles that you can use. So this gives us a way that a developer can log into an account with a read-only role so they can see what's going on in the cell, but not accidentally make any changes to it. And then maybe we have some elevated roles that give them slightly more permissions if they need to do some action to fix a problem when they're in their on-call. This is a screen, another screen from SSO that shows like some individual permission mappings for a given account. One thing that's really nice about this is that they have APIs for managing all of these permissions, which means that you can use the same CDK constructs that we've been talking about earlier in the talk to automatically manage this set of permission mappings where you're giving all of your developers a certain set of roles that they can use to access the accounts. So basically, since we already have this account registry that we built up that has a list of information about all of our cells and all of our developer accounts, we can use CDK. We can just basically write a little for loop that loops over all of those cells and grants the appropriate permissions to each developer. That's actually the inbound permission. So I said this in the wrong order. But that gives the developers the ability to hit access logs and other things like that. And then for outbound permissions, the cells may need access to a certain ECR repo in order to pull down the latest Docker image when a deployment is happening. They may also need access to certain like shared VPC networks for monitoring or other purposes like that. So you can also use, in both cases, since we've got this account registry that has all the metadata about all of our cell accounts, and we can use our favorite programming language with CDK to just loop over that. It's really easy to just define the permissions that we need for both inbound and outbound in code. And then if anytime we add a new cell or add a new developer, all we have to do is just let the CDK code run again, and it'll automatically set up the new permissions appropriately for the new cell or the new developer. So it makes it a lot easier to manage as your number of cells grows or your number of employees grows. So that's really all the interesting stuff there is to talk about with regards to permissions. We basically solved it at Momento using AWS SSO plus this account registry that we've been using for a lot of these, and then CDK to manage the mappings of the infrastructure resources. So that's really all that I wanted to cover in the talk. I hit these additional benefits a little bit last week, but I'll repeat them again briefly here. Doing this kind of automation gives you a lot of agility, which can be really powerful for your business. If you have a situation where you need to add a new cell quickly, it makes it really easy to do that. If you have a new important customer that you really want to make sure that their workload is isolated, it's really easy to spin up a new single tenant cell that they can be isolated in. And this infrastructure that we've built out means that we can easily add that to our deployment pipelines. And then the developer cells, we talked about last week about how a lot of times you'll find that companies will try to create some shared developer environment that engineers can use when they need to test their complex changes. If they're testing a change that involves two different pieces of infrastructure, it may be impossible to test that locally on your laptop, and you have to have a semi-realistic deployment of your application to be able to test it safely and correctly. But when people use shared developer environments for that, there's always this problem where different developers are working on different things at the same time, stepping on each other's toes and kind of breaking things out from one another without knowing it. And this pattern allows you at least the option to just stamp out a whole cell for a developer in their developer account really quickly, and they have an isolated place to test their changes, do benchmarking, stuff like that, and they can just tear it down when they're done. So to kind of wrap up here, there's no one size fits all for all this stuff. I talked about different tools that we use at Momento to solve different parts of this problem. But for any one of those technologies that I discussed, there are lots and lots of options out there that you can use to kind of slot in to the same general pattern that I described here. So if you're using GCP or Azure instead of AWS, they have similar services for most of the tasks that we would want to achieve. And then for the infrastructure as code stuff, there's lots of different solutions out there depending on what environment you're in. And then for CI/CD, there's tons of third-party options out there like GitHub Actions, Jenkins, and so on. So it's easy to kind of mix and match these based on what works best for your organization and what technologies you're using. Key takeaways. Cellular architecture has a lot of benefit for your customers, especially in terms of minimizing the impact of any outages that you might have. And it can also have a big impact on your engineering velocity if you do a little bit of work to set up the infrastructure for it in an automated way. We talked about the different problems you need to solve in order to have a really easily automated cellular infrastructure. Automation is a lot simpler nowadays thanks to IAC++. And then no one size fits all. You can pick and choose which tools work best for you and also how deep to go with the automation. It may make sense at your organization to do even more automation than what I described here that we did at Momento, or it may make sense for you to do less. And really, you can kind of pick the level that is going to have value for you and invest in it accordingly. So that is the end of my talk. And I wanted to thank everybody for joining today. And please feel free to reach out to us at Momento if you have any questions or interested in more conversations about this. And please keep an eye out for more Lunch and Learn talks. We have lots of them going on, including really cool stuff about vector indexing. So hope to see you all at some of those.